too much hand tuning. So Larry's going to go into the details of things called huge pages and how transparent huge pages are daemons that run automatically, and to give you an x86 2 meg page, etc. TuneD I'll go through briefly. CPU Affinity has been around pretty much forever in Linux, which, being an old hardware guy, I like to be able to control the destiny of where you go and get scheduled to. So we just heard about new schedulers, but in general, most users don't want to have to manually tune. So lots of improvements there. NUMA pinning, huge x86 over the past 10 years as well. So non-uniform memory is part of almost everything. Pretty much, then probably the next gen laptops are going to have multiple memory nodes. And then finally, how to also move interrupts around. So our team spends a lot of time on various workloads, various benchmark workloads, but Red Hat doesn't publish benchmark results, which is actually good. We just want to make sure people that use Linux have the ability to do the tuning, do the optimizations they want, and let the open source world compete with actually open source code as well. So, so we study this stuff with databases, Java engines, low latency fields across the variety of things, and the tuning actually comes in about 2 different flavors. Next slide, Larry. Next slide again. So TuneD was a thing we invented in Red Hat 5 initially, and it became a product in Red Hat 6. Not a product per se, just a package that basically collected a lot of sysctl parameters together to tune things for usually 2 categories, either latency or throughput. And I'll show you what that means in a second. So in Red Hat 7, we actually do turn on what's called a throughput profile. So a default RHEL 7 system is more geared to, we think, more of the average application prefers throughput. And next slide. So here's kind of like the difference. What's the difference between latency and throughput, right? So latency to me is how fast you can get from point A to point B. I was able to drive on the Autobahn recently, and that was quite a thrill because we didn't have a speed limit, so as fast as your car could go. But take one person, put it in a car, get there, right? Where throughput's the other side, either more lanes in the highway, how many packages can you put into a truck, say, and get them all from point A to point B. And so that usually involves some sort of aggregation at the software level, and that usually hurts latency. So how can you sometimes can't actually tune for both automatically, although you developers do give it a fair shot to give the best of both worlds. And final slide is, so there are latency TuneD performance profiles. On the right-hand side, network loads tend to be one of those cases that are most sensitive. If you want latency, don't aggregate all my packets together with NAPI. That's great to fill up the wire, but it's not necessarily, if you're that first packet in, you don't want to have to wait for all the other packets to fill up before that's shipped over the wire. So latency is more tuned for that small packet, and things like NFV and other use cases. Here are the differences, and these are all user mode. You're welcome to log in, use them. Set of the tuning. And Larry's going to go into the guts of it, so I think I'll turn it back to you, Larry.
Well, you've just got one more. You want to talk about that a little bit?
Oh, yeah. So does this matter? Does it really help? Let's look at some lab data. So by default, oh, wait a minute, that only helps the XFS file system? Well, actually, like changing the deadline elevators on storage, bumping up read aheads, doing some of these tuning values to have a better out-of-the-box experience. It turns out all the 4 file systems we support and ship with our OS here, GFS is a clustered file system, so it has some extra metadata overhead, but the point is that having it with the TuneD profile set to throughput actually helped improve performance across the board.
Okay. So what I'm going to first of all start out is talking about NUMA systems. One of the biggest areas that we get performance improvements or performance disasters is understanding NUMA and understanding how it works and how the memory access times and so forth, which, by the way, the next presentation is going to get into a lot of the details of that. So what a NUMA system is it's made up of building blocks that are interconnected. Years ago, when they invented SMP systems, they started to realize the more CPUs you stuck on the system, the more saturated the bus became. And you got to the point where if you added CPUs, you actually got nothing out of it, and added even more CPUs, you slowed it down. So they started creating systems that were built of smaller computers, so to speak, that were interconnected with high-speed buses. And the benefit is you can get several CPUs all running at very high speeds at the same time. The downside is if you're doing memory access that is not local to the node, then you get performance degradation because there's a lot of data and bus access going across these links. So it just allows much larger systems by distributing the memory and CPUs. Local memory access is obviously what we're trying to optimize for versus remote memory access. Most systems now are NUMA, and like Shaq said, within a very short number of years, if not now, all systems will be NUMA, and there's no way of getting around it. So we have to do a really good job in the kernel and in the tuning profiles and so forth to make sure that we get the local memory access. And we've been, over time, we've been doing an increasing amount of automation to make this automatic. Unfortunately, there is no one solution that fits everything. So at this point right now, we still do a fair amount of tuning in order to get the optimal performance. So the first thing I'm going to talk about is some tools. Just a couple of very simple ones. LSCPU, you can see this is the same system. LSCPU just shows you a 4-node system. It iterates the CPUs, enumerates the CPUs, down to, and describes the cache sizes and all this. And then NUMACTL with a flag -- hardware will give you a similar picture, but it also gives you a very important piece of information called a slit table down in the lower right, which is the cost of doing memory, both local and remote. So it's normalized to 10. So if you're on node 0 and you're accessing the memory on node 0, you get a factor of 10. If you go off node, then it slows down, the memory bandwidth slows down by a factor of over 2. So this is basically, it's basically a picture of this if you go off the node. On some systems, I just wanted to say, it might not even have this X in the middle. So in order to go from node 0 to node 3, it might have to make 2 hops. And if it did have to make 2 hops, the node distance from node 0 to 3 in that table might show something like 31 or 41. It could be that much of a slowdown. So then there's a utility called LSTOPO that shows you this in a graphic format. It shows you the same information, but in a graphical format. The utility NUMASTAT was at least enhanced by Red Hat, and it allows you to look at a system and really understand what your memory access patterns are looking like and what you're getting for local versus remote memory access. If you have a system that is, say, 4 nodes, you're running 4 processes. If you just let the thing, just start them all up and don't do any NUMA work at all, then you end up with what's over on the left here. I guess you end up with this. So basically what happens is, say, this process 37 runs on node 0s, and then its memory is distributed across multiple nodes. So on the order of 30%, 35% of its memory is local. The remaining 60 or 70% is remote, so you get a performance degradation associated with this. If you do a good job, though, you can get the processes, if they fit on a node, they either are utilities, manual tuning, or are utilities, or the kernel and later kernels will force it onto the node, and you'll get total local memory access. And this NUMASTAT utility basically shows that. So in this particular case, it was a 4-node system, each running 4 versions of KVM, and you can see basically the number of megabytes that are distributed on each node if you did absolutely no alignment or nothing at all, versus if you either manually pinned it to the nodes, or you let a utility, and I'll talk about that in a minute, or the kernel and later kernels move everything around. Then it'll move everything around and do all local memory access and no remote. Obviously, if you overload the system there are more processes, more memory demand than there is memory on the system, it's not going to look as pretty as this, but it still basically works. So good tips for good NUMA performance is there's a lot of NUMA systems have a BIOS flag that allow you to turn NUMA off. And we actually have some performance results that are better with NUMA off. And maybe I'll talk about that a little bit toward the end. But basically, you don't want to turn it off because in the hardware, there's no way of disabling NUMA. The hardware might be able to do something like every other cache block is distributed among every other node, but there's no way of centralizing it all to one location. Turning it off will make the operating system, make the kernel boot up as if it sees one node and it won't have any knowledge of the slit table whatsoever and won't be able to do anything. Know the workloads, so if you're running multiple instances of KVM on a host or something like that, to understand the size of them, understand the topology and so forth, and make sure that you're aware of it and you do all the right things. Did you want to say anything about this guy right here? This is an example of.
Yeah, sure. So what Larry's alluding to in RHEL 6, he was comparing the schedule of RHEL 6. In RHEL 7, we're going to talk about an auto NUMA scheduler that's also on by default, and again, been pushed upstream a few years ago. So how can it actually help? Again, so proof is in the output of actually running multi-stream workloads, in this case spec floating point streams, and it's a whole suite of different applications, and they all have to run simultaneously, and it pretty much has to saturate the cores. So the blue bars show that if you did not apply NUMA tuning, you would be leaving significant performance on the table. And in fact, more recently, you see the gain in the red bars is, what is that, about 35% performance on the same system by getting this scheduling, and hopefully the auto NUMA scheduler. And RHEL 6, you're going to also talk, I think, about a user space daemon called NUMAD. It is real.
The next thing I wanted to talk about is the way the kernel processes NUMA information. The kernel itself has some of its data structures are based on a per NUMA node basis. So even the kernel is very careful so that if you run a process and it starts on a given node, then a lot of the page allocator, the slab cache, a lot of the memory allocation code is NUMA aware. So it will, if you fork a process that starts running on a given node, it'll allocate the kernel stack and a lot of the slab cache data structures and so forth, so that when you trap into kernel mode and start doing a bunch of kernel activity, even the kernel will run NUMA aware. So it does interrupt processing, I/O and DMA capabilities are NUMA aware. The memory zones are NUMA aware. The page reclamations, okay, there's a K swap D per NUMA node, and they run independent of each other, and I'll get into some of that. That has some strange consequences if you're not aware of it or if you do the wrong thing. And there are a lot of other NUMA aware threads in the system. You may need to check the status and look at times. If you're really trying to optimize and get a good performance result, you may have to really be aware of the way the NUMA system, the way the hardware is laid out, and the way that the kernel is distributed among that, and the user space is distributed among it. So the first thing I wanted to talk about is the way that memory is laid out. In a very simple two-node x86-64 system, node 0 is going to have 3 zones, just like it has in a non-NUMA system. It's going to have a DMA, a DMA32 zone, and a normal zone. And then node 1 is going to have only a normal zone. So what this implies is that the K swap D that runs on, say, node 0 is going to have to deal with 3 zones, where the K swap D that runs on nodes 1 through n-1, where n is the number of nodes, only has to deal with the normal zone. So there is also, the paging dynamics also are NUMA aware and work on a NUMA node basis. So basically, this algorithm right here that allocates memory from the free list and doles it out either to the page cache or for anonymous memory, and does paging and swapping and dirty write back and so forth, happens on each node. What this implies is if you have multiple nodes, one of the nodes becomes exhausted where the other nodes are not exhausted, you can have swapping going on one node where there's no swapping going on another. You'll take a utility like VMstat and you'll see it with potentially many, many gigabytes of free memory, yet it's swapping. If you see something like that, that's indicative of one of the nodes being exhausted, the other nodes not being exhausted, and there are ways of working around this and dealing with this. But the next thing I'm going to talk about is when Shaq first talked about Tundi, Tundi is a automated daemon that takes and for each profile sets a bunch of kernel tuning parameters. And I picked a half a dozen or so of these kernel tuning parameters. I'm going to talk about how they interact with NUMA and what we do to get optimal performance out of the system. And I guess we're just going to go from there. So I grabbed like a half a dozen of them that you'll see in a lot of the Tundi profiles. So I was going to say that all of these are documented, by the way, in documentation/VM or documentation/kernel. In the documentation area, they're well documented, and we've enhanced the documentation to talk about how they interact with NUMA systems. So the ones that I want to talk about that are dependent on NUMA are just three of them: the zone reclaim mode, the swappiness, min-free k-bytes. I don't know how many people in here have messed around with some of these tuning parameters, but these three depend on NUMA, or they interact with NUMA, I should say, where the independent ones, like the VFS cache pressure and the two dirty ratios that control write back, are system-wide. They don't really depend or have an interaction with NUMA at all. So the first one I want to talk about that you'll see in the Tundi profile is a flag called zone reclaim mode. This flag controls what happens when a given NUMA node runs out of memory. It's got two choices. It either hops onto the next node and starts allocating memory there, which is going to induce cross-node memory references when the application runs, or the other choice is to stop and start reclaiming memory on that node and start swapping and paging and dirty write back and so forth on that node while the other ones aren't doing anything or don't have any page reclamation going on. This flag is probably the most important or performance-sensitive flag that you can run into. It's set by default at boot time, and it's set based on that slit table. If the kernel determines that that the average cost of cross-node memory references are more expensive than reclaiming memory over the long run, then it'll turn this flag on so that it'll go off and so that it will do local memory reclaiming versus hopping onto the other node. And this is also a trade-off of if you have a lot of short-running applications, they just run for a while, you fork a process and it runs for a second or two and then terminates. There's little benefit to having it swap and page and reclaim memory on the node versus if you have a long-running application like a database server that's going to be up for a long time, it probably makes a lot of sense to pay the penalty at initialization time to get that thing to reclaim memory and fit it on the node versus doing remote memory access. This just going to talk a little bit about this. You can see what it's set to by looking in Proxys VM, zone reclaim mode. You can turn it on and off dynamically on the fly without rebooting the system. It's set by default based on the NUMA factor and the way that Red Hat has done the development of the automatic NUMA code. We have turned it on and off on various releases along the way, or the default on and off on various releases along the way. And if you look at some of the Tundi profiles, they'll flip it back on or off the other way depending on what the profile is, if it's latency sensitive or bandwidth sensitive. So this, basically what this shows is the consequences of not setting this thing correctly. So you can see if I guess this is just a bunch of benchmarks, right?
Yeah, this is again the spec suite again, and the effect of if the workloads are running and essentially exhausted physical memory if you had the zone reclaim mode set, the cost of essentially swapping on the same node is very painful in performance versus the baseline is allowing it to schedule memory across the NUMA node. So yeah, so if anyone experienced Linux swapping on your laptop's PC, you run out of memory and
Nobody ever experienced it.
Okay. Anyway, we'll keep going.
Okay. So the next parameter I wanted to talk a little bit about, and these are the ones that you'll see a lot in these TuneD profiles, and you'll see them on in some and off in the other, or adjusted in some in one way and adjusted in the other. The next one is called swappiness. This is the typical, this parameter controls how aggressively the system reclaims either page cache memory or anonymous memory. It's an integer, and it's set between 0 and 100. If you lower it, lowering it causes it to avoid swapping and then therefore reclaim the file system cache memory, the page cache memory, much more aggressively than the anonymous memory. Increasing it just does the opposite. So if you go back to that little picture that I had that had the page cache and the anonymous memory, it determines who contributes to the memory that's going to be freed when the system runs out of memory. And it also what I was going to say is each node uses this thing individually. So in other words, the kswapd and the page reclaim code, even though it's a global parameter, if one node has a lot more page cache memory and a smaller amount of anonymous memory, and the other one has the opposite, it's going to act based on the global setting. So, and this is important to know as you look at these systems. If you see a system that's swapping, but there's a lot of free memory, then chances are this parameter right here is the one to go to and adjust. And like I said, this is set in almost all of the TuneD profiles. And it's, once again, it's an integer between 0 and 100. The lower you make it, the less aggressively it swaps. The higher you make it, the more aggressively it swaps. And what it does for one, if it swaps aggressively, then it does not reclaim page cache memory available as aggressively. So if you get something that has a big file system footprint and you don't want the file system cache reclaimed, you want it hot and staying in there all the time, you'll typically increase this so that it'll swap and reclaim anonymous memory and leave the page cache alone, and vice versa. Then the last thing I wanted to talk about here in the memory reclaim code, the memory tuning, is the free list watermarks. Like I said, this exists on every node in the system. So there are 3 watermarks, page reclaim watermarks: min, low, and high. So when you start off life, all the memory is free, and as the memory gets used, it gets chiseled down to high. Once it doesn't do anything until it crosses down to low. After it crosses low, it wakes up kswapd for that node, and then kswapd works very, very hard at trying to free memory back up to pages high. However, there's one thread. kswapd is one kernel thread per node, so what can happen is you can overwhelm it. And if that happens, the free list goes lower and lower until it hits min. Once it hits min, basically every process becomes kswapd. It starts running the same code. So before it will let you have a page of memory, it'll force you to free a page of memory, or it does it in batches. It forces you to free a batch of memory before it lets you have any of them. So these 3 parameters here that have a really profound effect on the way the system runs when it runs out of memory. Does it fall off a cliff, or does it actually degrade with some elegance? And so those 3 parameters are controlled by a tuning parameter called min-free k-bytes. And what min-free k-bytes is, it's this. So if on a NUMA system that has like 4 nodes, if min-free k-bytes is set to some value, that value is divided by the number of nodes and then distributed through each of the nodes. And then the distance between min and low and high is scaled up accordingly. And you can see this if you play around with the tuning parameter. If you cat out min-free k-bytes, you'll see it's set to, this is a number of kilobytes, so it's 90 megs. And on node 0, the sum of these is equal to the actual minimum. And so basically half of it is on node 1, and the other half is distributed between the 3 node zones of node 0. And then the distance between min and low and high, as you increase this, scales up accordingly. So if I went in here and doubled it, and you can see these values doubled, as did the distances between the two watermarks. So in some of these TuneD profiles, you'll see it will be set. So what this does is increasing these values is generally a bad thing to do, because if you increase min free k bytes, the only processes or code that can allocate memory below min are privileged kernel threads. So it's effectively like removing memory from your system. So you don't want to crank this up to gigabytes. You want to do a little bit at a time, which is what the TuneD profile does. But also what it does is when the system runs out of memory, it doesn't fall off a cliff. There's a gradual degradation. So this is basically like a trade-off between throughput and latency. So the other thing I wanted to talk about here is there are, as far as NUMA tuning is concerned, there are 3 different solutions. You can either manually, actually there are 4. Just don't do anything about it and let the cards fall where they may. You can, in earlier versions of Red Hat Enterprise Linux, we had a user space utility called NumaD. And what NumaD would do is it was user space, so it would actually use CPU and memory C groups to try to move processes to the different nodes. So it would create 4, if on a 4-node system, it would typically create 4 CPU/memory C groups and move processes between them if it noticed cross-memory references. And basically what this is, that's what this does. It's a user space process or user space program, and that's how it works. In Red Hat Enterprise Linux 7, which is a 3.10 base kernel, the 6 is a 2.6.32 base kernel with a bunch of backports from upstream. But anyways, the RHEL 7 kernel has it built into the kernel itself. So the kernel is the one watching and moving stuff around, so you don't have to run something like NumaD, which creates the overhead of the C groups and all this stuff. The kernel itself is doing it for you. It just does it basically does it on the fly. However, there are TuneD profiles that shut the NUMA balancing off, because there are cases in which you have very large applications that span several nodes or consume the whole system. And the kernel NUMA balancing code might sit there and fight with itself, moving processes from one node to the other, and even though there is control on how aggressively it moves them, in some cases we get the best performance by just simply shutting it off and hand pinning or something. You want to talk about this?
Yeah, that's right indeed. We are definitely working to make even the large loads have no low overhead, but it's AutoNUMA does have to scan pages to look for opportunities. Auto balancing, though, should be deciding at schedule time, which NUMA nodes, so dynamically, much less overhead than doing it in user space. The other reason, and so you can see again some gains here. This was actually a set of the Bench BWEML is a SAP application, and by having AutoNUMA set, so this particular vendor never wanted to do manual pinning, and so again, the bars are the performance, the line going through is the right-hand side is the percentage gain, the right side of the chart. So you can get substantial gains. One other case to turn some of these automatic daemon transparent huge pages or AutoNUMA off is to keep determinism straight. So you'll see some of our low latency profiles disable some of these more exotic features because you basically don't want daemons popping up in the middle of potentially low latency applications.
Yep. And just one other thing I wanted to say is this basically illustrates how much better the current automatic kernel balancing works than the
Not at all.
Oh, that wasn't with anybody?
No.
That was without it. Okay, sorry. So the next thing I wanted to talk about is some of the way the CPU scheduler works and its tunables. I won't get into a lot of these, but there's tunables in the scheduler that control things like the quantum and how quickly the system will decide to move from one CPU to another. This really becomes a lot more complicated with NUMA systems because, for instance, there's like some of the fine-grained scheduler tuning in RHEL 5, there was the equivalent of a quantum. The quantum really doesn't exist in the later kernels, so it's divided into how frequently the system looks at waking processes up and how frequently it looks at putting them to sleep. I'll talk a little bit more about this later here. There's something called load balancing. If you have all your CPUs have something running on it, or have several processes running on it, so the load average is significantly above 1. If one of the CPUs goes idle, initially you might think like, oh, we'll just move some of the processes to the other CPUs and start running them. On a NUMA system, that can cause this imbalance to occur. This can cause cross-memory references to occur. So rather than just simply blindly doing this, there are parameters that are adjusted by TuneD in the scheduler that determine how much time it's going to allow the system to remain in this imbalance before it goes and starts shuffling stuff around. And these, once again, are adjusted. They're well documented and adjusted a lot in the TuneD profiles. There's another one called child runs first. This is a parameter that determines when you fork a process, if the parent sits there, if there's not enough CPU available for both the parent and the child to run, who runs first. And once again, this has a fairly profound effect on a NUMA system because it might decide to run the child on another process, a processor instead of itself. And once again, I'll get into some of this in a little bit of time. And then the other area that I wanted to talk a little bit about is file system and disk I/O. Do you want to talk about these?
Sure. Just when you thought you understand the bars, if you go back, bar charts, if you go back to, this benchmark was done in time, so lower is better. So the red bars are better, lower being better in here. But the same thing, the line across is the percent difference of altering the sched migration. And so just briefly on disk I/O, a couple slides here in the future, Larry. We'll go back. And so really, like to run huge applications all my life with our team, and the ability to choose, just like we were sharing about CPU scheduler, dynamically changing quantums and stuff for CPU. Well, now you can dynamically change which I/O elevators, they call them, or I/O schedulers. So CFQ was for completely fair scheduling, and it also was mostly for interactive response times for maybe laptops. But back in the data center, we just had a talk on deadline scheduling for CPUs, but the deadline I/O elevator has really been determined on at least more modern storage hardware to be one of the best because it, again, has the input queue and output queue and can schedule those deadlines, still allows the I/O stack to do aggregation and things, and again, that's our default in RHEL 7. So the no-op, again, you see that being used for really high-end and SSDs, so like NVMe cards and NVDIMMs and stuff like that, and then and there used to be a fourth one that added a delay, and fortunately, I think we no longer support that one because I would never try to tune that because it adds a delay for every I/O. But I'll let you go, Larry.
Okay. So, and then the next little section I wanted to talk about were some of the parameters that you see adjusted in the TuneD profiles a lot that are really not NUMA related, even they do have some NUMA effects. And they are the dirty write-back parameters. There are several of them, but I'm only going to talk about a couple of them here. The background ratio and the dirty ratio, and then there's some read-ahead parameters that are also, they're system-wide and they don't have a lot of effect on NUMA, although there is some. So basically what happens when you open a file and start writing to the file, reading and writing to the file, the contents of the disk, obviously from the file system, are read into the page cache. So when you start doing file system operations, you're just sitting there doing memory accesses, copying from your buffer to the page cache and vice versa. If it's an M-mapped file, it's not copying. Those pages in the page cache are just simply mapped via the page tables in user space, and it's just updating the page cache on the fly. And it sets dirty bits in there. When you do a file system write operation, it copies over data, sets dirty bits, and then later on in the background, it's a write-back cache. So later on in the background, it starts flicking the pages out, and the more, depending on the tuning, the more pages are dirty, the more aggressively it happens. So, so the two parameters that control this are the dirty ratio and the dirty background ratio. And this is basically if you do a sync, basically it writes out all the contents of the page cache, writes it back to disk, and you start out with 0% of the page cache being dirty. You start doing file system write operations, and those pages start getting modified, so this percent of dirty goes up. At the same time this is happening, by the way, the old equivalent of the update daemon which is controlled via a couple other parameters, writes everything out that is some number of microseconds old, and it does it every certain number of microseconds. And the defaults are like 30 seconds and 5 seconds by default. So anything that's 30 seconds old in the page cache gets written out by a different mechanism than these. So basically, but over time, you can get to the point where the background ratio, the lowest one, which is 10% by default, and that's changed on almost all the TuneD profiles. Once you exceed that, it wakes up these background daemons that start flicking the page cache pages to disk. And then it works very hard on keeping us down to this level right here. And then between here and here, once again, it's like the update daemon that's flicking those pages out. Well, once again, there's a limited number of kernel daemons that do this. And even though they run on a per NUMA node basis, they're all pretty global. They're all working in unison because even though those daemons do write the pages from a given node to disk, each individual one of those do that, it's possible that several different processes running on several different nodes could be contributing to them. So the two are sort of independent here. But after a while, what can happen is you can overwhelm this mechanism to write stuff back. And just like the page reclaim code, once you exceed this dirty ratio, the higher two, or 20% by default, then the you should use that Hawk and Yankee on this stage. So once you exceed that level, then the process stops, and it stops just writing to the page cache, and it's forced to do the same work as the page writing daemons, and forced to do. So it actually throttles the writing at the same time. And once again, because even that can be overwhelmed, these are usually set to 10 and 20% by default, but these TuneD profiles adjust them. And this is you can almost look at this as another trade-off between throughput and latency. If these are set really low and you don't allow much of the page cache to be dirty, then it does a lot more frequent write-outs, and the work that it does is small. So that basically decreases the latency, but also decreases the throughput. You don't get as much work done. Whereas if you crank these things up really high, you'll get a lot more work done between iterations of this, but when it comes time to pay the piper, you do a lot more work on writing this stuff out. So you get latency spikes out of this. So you'll see the latency sensitive will pull these things down, the throughput sensitive will increase them. And this just tells more about how they work. Everybody's probably familiar with these things anyways. This controls the flushing of pages. And there's also another, with very large systems, we support terabytes of physical memory. Sometimes you want to set this on a lower level than 1%. 1% of a 12 terabyte system is a fairly large amount of memory, and you might not want that amount of memory to be to be the threshold. So you can actually control it in terms of bytes. So if you want to go, say, less than 1%, you want to get a less than 1% resolution, you can control it with bytes instead of with, and you'll see that stuff in the tuning profiles too. I'm not sure we want to talk too much about this, but if...
10 minutes, go ahead.
Okay. So the next thing I want to talk about a little bit is the page sizes in the kernel. The Intel hardware supports 3 page sizes, 4K, 2 meg, and 1 gig. And there are multiple ways of using these. By default, we use, typically we use 4K pages. There is a mechanism that in which, via huge TLBFS, you can decide to use either 2 megabyte or 1 gigabyte pages. I'll get into that in just a minute. And there's another mechanism that'll automatically do it for anonymous memory called transparent huge pages. These things are turned on and off in these TUND profiles a lot too, because there are consequences to using big pages. If you have a big page, obviously each TLB entry maps between 4K and 2 meg, it maps 512 times as much information. So you get a lot more, information mapped. Whereas if you have a, but the downside is if you touch 1 byte in that 2 meg page, it instantiates a whole 2 megabyte versus 4 kilobytes, 512 times as much. So depending on the application that you're running, it might be desirable or not to have these on and off. And once again, they'll be turned on and off in these profiles. So this is just basically how you use standard 2 megabyte huge pages via huge TLBFS. You'll see a lot of scripts that do this. Typically don't do it by yourself, but like database scripts will do it. It'll echo a number into Proxys VM and our huge pages. And then if you do a cat meminfo, proc meminfo, you'll see how they're used. If you actually use it, you'll see the free becoming reserved and then actually used. What I wanted to say that on a system that this stuff was all designed before NUMA sort of came into the picture. And if you say I want 2,000 pages, if you say I want 2,000 pages, if it's a 2-node system, it'll go out and put 1,000 on each one of the nodes. So that's basically what this shows, is if you say 1,000 in Proxys and our huge pages, then it'll put 1,000 as a distributor on each node. Well, with NUMA, especially if you're going to run a database on node 0 and you want the SGA, the Oracle SGA on node 0, then you probably would go into the sys file system allows you to control and see the NUMA parameters a lot more accurately. So you can see that you can say, I want all 1,000 of them on node 0, and that's where they are. The transparent huge pages are a mechanism in which the anonymous memory uses 2 megabyte pages. And as you can see, when it's on by default, you run an application, and if you shut it off, you can say I don't want to use it. You shut it off, and you can see the system time off versus on is almost twice as much. You get a big performance drop on doing this. But once again, the downside is if you have a very sparse memory reference pattern, the performance benefit might actually exceed the cost of doing that. And then finally, 1 gigabyte pages. Up until recently, they were allocated at boot time. If you allocated them at boot time, you could never get them back. Once again, they're exactly the same as the 2 meg pages. They're just 512 times larger. They're always scaled up by a factor of 512. On RHEL 7, in the upstream kernels, you don't have to boot the system. You can actually allocate them at runtime. Allocating them at runtime, there's a daemon that runs in the background that coalesces memory together, moves everything around, and builds a bunch of very large pages, and that's how this code works. So you can allocate them and free them after boot time. However, if your system is up and running and a lot of memory has been allocated, it might not work. If you really want a lot of them, the memory might be wired, the kernel might be using the memory, and it might not be movable. So it's better to do it earlier versus later. And then the last thing I was going to talk about, if I get time, is C groups.
Being a performance talk, it's how many slides per second, Larry?
Well, we got until...
We need quick.
Yeah. There's no questions on any of this stuff. So anyway, so there are two different mount points. In the older kernels, RHEL 6, you can see the mount points were in Etsy, and on RHEL 7, they're in the sys file system. But they basically they're very similar. And in terms of what a C group does, these are the foundations of containers. And that's why it's really important to understand this stuff and know that you can build subsets of your system using C groups or containers. And so say, for instance, this is just a really simple thing that was easy to do and easy to see. I had a 16 gigabyte 8 CPU system, which is obviously really old in today's standards, and I wanted to create a 2 gigabyte 4 CPU subset of that. This is basically what you do. You go into the C group and you create another C group down in the hierarchy. You go down there, you set, this mem sets the NUMA node. The CPUs are the CPUs that you want to run on. So if we went back and look at that first example, node 0 had CPUs 1 to 3, node 1 had CPUs 4 to 7, and so forth. And then I say I want to limit it to 2 gigabytes in size, then run all the processes in there. And you can see that even though I fired up 110 processes, it ran all 110 of them on only half of the CPUs, and the other CPUs are idle here. And you can go even further. What I did want to say is that the way that a lot of this tuning is done, especially when it comes to containers, is you can use the C group, the memory and CPU C groups, to control the NUMA binding. So what you can do is you can say, one that's done correctly, so to speak, is node 0, CPU 0 to 3, and then you run a program. You can see that when you start out you can see basically that you get all hits. In other words, local memory accesses and no increase in misses, which is a remote memory access. And if I do it actually at 100% wrong, so I say I want to run on CPU 0 to 3 on node 1, which is all remote memory accesses, and do the same thing again, the hits doesn't change at all. It's all the misses that change, and that tells you that you're out of time. I don't know if we want to try to scurry through some of this or answer questions, or what we want to do.
You have 5 minutes for questions, so you can either talk or...
Do you guys want him to finish? He's only got 2 or 3 more slides, or do you want questions?
Probably 8 slides to go. So and then we're kind of on the same thought as the schedule of talk before here. So there are, inside of the CPU C groups, there are multiple scheduler options, one of which is the shares. So in the case of shares here, you start out, you create a CPU C group, it has 1,024 shares. And if you say, I only want to allow this C group to get 1% of the shares, you basically turn it down to 10. So 10 divided by 1024 is about 1%. So if as long as nobody else is using the CPUs on the system, then it will allow, it will throttle this to 1%. So you can see that it only, so I wrote this program called useless, and all it did is a while one. And I ran like 99 copies of it. And I wrote one called useful, which did the same thing. And you can see as long as all these useless processes are running, it'll throttle the useful one to 1%, just like we told it to. And then this is basically an example of Oracle. If I forget time, I'll go back to this. And then the other type of CPU-C group that is used in these profiles a lot is the quota. So in the case of the quota, it's just the opposite. You start out with, there are 2 parameters here, period and quota. And the period is set to 100,000, the quota is -1, so that's off. So basically what you can do is if you run a program or a set of programs that consume all the CPU, if you told it don't throttle it at all, even if regardless if anybody else is using the CPU, it uses all of it. But if you say, I only want to use 1% of it, so in the quota, you put in 1% of the period, even though there's nothing else running on the system at all, it'll only use 1% of the CPU. And then this section right here was just talking about OOM killing that happens in C groups. You can, once again, OOM kills are what the system does. If it's backed into a corner, it runs out of all the resources, and it has basically 3 choices: hang, crash, or kill the lowest priority task. And the choice by default is to killing the lowest priority task, and it's called an OOM kill. And when that happens in a C group, so basically what I did is I set this thing up, so I said I want to set you can control how big the memory is in a C group. So 1 gigabyte of RAM, 2 gigabytes of swap space. I run this program that allocates and chomps on 16 gigabytes. So what's going to happen is it's going to try to touch all the pages. It's going to use a gigabyte of memory and then swap out 2 gigabytes, and then it's going to finally kill the process. And when this happens, you can actually see in the VM stat when the kill happens, then it puts all the memory back on the free list. And in the dmessages file, the difference between one that has been killed because of a C group limit versus a global is it'll tell you that task in /test, which is the name of the C group that I created. It'll tell you the reason that it killed the process. I don't know, you want to say anything about the summary here? This was a lot of information to swallow. I understand that.
It's a week-long class that I'm not kidding almost, but yeah, no, I mean this is a good summary. I think probably if you guys do have, I mean you can read it for yourself. If you guys do have questions, yeah, I'm sure we can probably try to take them outside the room. Is that what?
Yes, please.
Okay.
I think we're in everybody's way, so. This is, like I said, it's a lot of information to try to show in a short period of time. This stuff is all well documented, but we tried to give you an idea of when we have these 2D profiles, where we get this information, where we get it from, what we adjust, and there are many more than these 6 parameters, by the way. There's a couple dozen that we adjust all the time. And so, anyways, I think that's it. What's that?
Yeah, he's a wild man.
It was not only full of people as a session, it was full of information as well.
I know, it's no way
Yes,
to do
and
this.
you started early, you know?
I know. Well,
That was a good
This
one.
usually takes, we usually do this in like a 2-hour presentation. We should have asked for 2 hours. If we had 2 hours, we would be able to get into examples and all kinds of other stuff, but it's just not enough time. Sorry.
No worries. No worries. It was a great one. Let's try to get this up and working. Let's see. Hopefully, you have a VGA of it, so I think it's going to be straightforward than these again. Some newer ones have had trouble. I think it's okay. Let's fire it up. Let's see if the thing is still in VGA. Okay, it's in VGA.
You know, I don't know. Oh, no, I'm sorry.